Hi, good evening. It is 6 p.m., but people are yet to join, so we'll wait for a little longer. Hi, Emma. We'll just wait for a little longer to allow some more people to join.
बारह लोग हो गए ना? नहीं, नहीं हुए, चार लोग हुए अभी। राकेश।
Good evening and welcome to the live session for the course Computational Science and Engineering. This is week one, and the instructor for this course is Professor Ashok Dey from the Department of Aerospace Engineering at IIT Kanpur. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. I primarily work in the broad area of additive manufacturing. So, our agenda for today would be introductions. Then we'll have a short recapitulation of the topics that were covered in this week, after which we'll solve a few problems, which I hope will help you to solve the assignment questions better, and also have a revision of the concepts that were covered this week. And for seamless communication, I would request that you keep yourself muted and raise your hand. Then I'll call out your name, and then we can discuss whatever point you might have. And please mute again once we are done. And please otherwise remain muted at all times. So before we go to the contents of this course, let's discuss a little bit about why uh, we are in this course, what is the importance, and what are the applications of the learnings from this course. So, for any researcher or even a student in general, you would find that often engineering fields can be explored via multiple ways. One of them is, of course, the experimental method, where we go into a lab, we have our equipment or our physical system on which we have a physical trial. We subject it to certain external stimuli or conditions and record the responses. And often, in the absence of any well-defined or uh, a priori known laws, experimentation is the only way to predict or gauge the behavior of a system. So, unless you go into the lab, perform a few experiments, and note the observations, uh, there is no other way. But often, uh, we resort to modeling a system, which has its own advantages. I'll come to that. And in the model, what we have is a mathematical representation or a simplified representation covering perhaps the most important physics of the phenomenon. Of course, the more uh, faithful the model is, the better will be its predictions. But also, it will be more difficult or more intractable to solve. Thus, we start with a simple system and then keep building upon it. The model is often based on governing equation or a set of governing equations, which are which describe the most important or fundamental physics behind the phenomenon. And it is in this computational model that computational science comes into the picture. And mathematics is the language of physics. So unless we have a very good grip on the mathematics of such computations, we'll not be able to make much headway. Some advantages which say a computational approach has over an experimental approach is that often experimental trials are time consuming, energy consuming, and cost ineffective. For instance, I work in additive manufacturing, and as you would be aware, the capital cost is immense. Uh, the cost of equipment itself, the cost of training, as well as the cost of raw material, be it wire or powder. Also, it's a highly power intensive process, so energy costs are also very high. So it's not always feasible to perform, say, more than 50 trials to optimize your window or to find out all uh, the phenomena happening across a parameter window. And thus, it's not always possible that you run all the experiments which you want to. Rather, it is easier that you develop a model, you calibrate it after doing a few benchmark experiments, and Then once you believe your model is accurate enough, you use the predictions from your models to say make further conclusions. Another uh, advantage that computational models offer us is that often there are certain say variables or certain uh, physical parameters which cannot be observed or recorded very easily in real time. Say when we are depositing material additively, the temperature field across the substrate or even in the most recently deposited layer, while theoretically it is possible to record it using say some thermal camera or some infrared camera with a high enough frequency, but practically it is very difficult. Also, several other effects come into the picture. Thus, it's not always physically, even though it might be possible, it's not probable to have these observations. But these things can be had from a computational model. Once it is validated and calibrated, you can extract all sorts of useful information from a model. Of course, the best approach is to go hand in hand, where you have computations, you have certain experiments to validate and to calibrate them, and they operate synergistically. Now, the foundation of computational science will include a lot of mathematics, primarily linear algebra, differential equations, both ordinary and partial. And as we move further into the course, I believe we'll also look at some of the implementation side aspects and some of the numerical schemes, how to implement them, what are some of the common errors, some computation, and as such. So in this first week, we'll look mostly at the fundamentals, which include. So Hema has put up a question: what is the scope of computational science? So Hema, the scope of computational science is immense. I'm not sure of your background, but if you are, say, a bachelor's or a master's or even a PhD student of engineering, you would know how there are fields, entire fields dedicated to computation. Aerospace engineering, for one, uh, utilizes computations in fields such as fluid dynamics uh, to find information about the flow field surrounding any complex body. And I mean, that is just one example of CFD. And see, the more complicated or harder the system, the more ways out to computation because experiments just don't cut it. So I am from mechanical engineering. I spoke about additive manufacturing. In aerospace engineering, we have CFD. Uh, we also have, say, this biological flows or in micro and nano flows where CFD is computational fluid dynamics is used extensively. So the more complex the system, the more physics involved in a phenomenon, the greater the scope of computational science. Because it's A, very difficult to perform those experiments. B, they may not really be, say, cost effective or even time or energy effective to perform. And thirdly, you cannot extract all the information you need just from experiments. So computational science comes in the picture. Now, for this first week, we'll review some of the topics that were covered. So mostly involving vectors, vector spaces, and matrices. So at the very outset, it is very important to note that our classical idea of vector would be say vector has quantity. It's a quantity which has what magnitude, uh, direction, and sense. So if it were only magnitude, it would be a scalar. This is the classical sense or the classical meaning of vector which we have developed via engineering or via our physics courses. But mathematically, a vector can be much more general. So, say rather than writing something like, say, I have an A vector with some components along the say three directions in a Cartesian coordinate system, I maybe simply denote it like this. where inherently I know that all these three numbers, that is 2, 3, and 4, represent the three components along the three principal directions or along the three coordinate axes in a 3D space. But what happens if I extend it to a 4D space? Say I have another vector, which is something like now. This is not as easy to visualize. Some of you might still be able to do it. But what happens if we keep doing this? What if we extend it further? Now, visualizing a physical quantity such as, say, a position vector, which is a straight line which has some magnitude, a direction, and a sense in seven-dimensional space might not be so straightforward or so intuitive. Mathematically, a vector is a more general quantity, and you may visualize it just as, say, an ordered n tuple, such as this one is an ordered triplet, this one an ordered quadruplet, and so on. So you have an ordered set of numbers or say quantities, and that order has meaning, and that is a vector. Again, another way to generalize the concept of a vector and look at it is just as a set of elements which we refer to as vector space, and that is the definition which we have here. So most of the content which I have on these slides are either taken from Professor Ashok Dey's slides, or they are from this book, Advanced Engineering Mathematics by Dennis Zell. This is the recommended reading here at IIT Bombay. Of course, you are free to refer to your own books or some of the texts which Professor Day has described in the course. Of course, the content would be similar. So we'll just go over a few definitions. These are theorems and definitions. We'll not look into the proofs. And the point of going over these fundamentals once again is to have more clarity with the topics that were covered and to be better able to solve the questions that were posed in the assignment of this week. I might not be able to solve the questions, I mean, the exact questions that are posed, that is against the course policy, but I'll try to solve questions which are of a similar nature, which maybe, say, utilize the same fundamental concepts and which will definitely enable you to solve the assignments by yourself. So let's get started. A vector space such as V is just a set of elements on which two operations called vector addition and scalar multiplication are defined. And if V, the vector space, is indeed a vector space, then it has to satisfy the 10 properties. These are the 10 axioms which define a vector space, such as for vector addition, if you have two vectors or two elements x and y in the vector space V, then their sum x plus y should also be in V. For all x and y in V, the sum should be commutative, that is x plus y should equal y plus x. Now, it might appear very, say, trivial at this point because of our classical sense of what addition and multiplication means. But we'll look into a few examples where we see that, say, addition is defined in a separate way. Say, rather than defining the addition of x plus y equals, say, simply just x plus y indeed, say 1 plus 2 or something on those lines. What if we define addition as xy or some x equals k or something on those lines? So you see these properties do not remain trivial anymore because then they must be satisfied. So it's very important to get out of our classical idea of what a vector is because mathematics can get very abstract and be very rigorous with the definitions and the axioms that we have. The third axiom that has to be satisfied is that the associative law, where for three elements or three vectors x, y, and z in the vector space V, the sum of x plus y plus z should also equal the sum of x plus y and z. Again, the fourth one is the existence of a zero vector. So there would be a unique vector 0 in the vector space V such that 0 plus x shall equal x plus 0 shall equal x. Is this zero vector always, say, 0? Like, say, whatever uh, be its dimension, is it necessary that it should always have the elements as zero. We'll find out in some time. Again, depending on how we have defined our addition operation or our scalar multiplication operation, we'll find out that the zero vector can take on different meanings or different forms. Similarly, the negative of a vector. So for each element x in the vector space, there exists a vector minus x or negative of the element such that their sum shall equal the zero vector. Important to note that this is the zero vector and not the number zero only. So if my zero vector say is something else, say if my zero vector is some 110 or even some arbitrary ABC, then this negative of vector sum should equal that vector and not necessarily a zero. Similarly, we have five axioms for scalar multiplication. So if k is any scalar and the element x is in V, then kx should also lie in V. Similarly, the distributive law multiplying the sum x and y by any scalar k should equal kx plus ky. Distributive law for scalars. So if you have k1 plus k2x, that shall equal or imply k1x plus k2x. Similarly, the scalars scale up. So k1 k2x equals k1 time k2 times x and so on, and 1x equals 1. So this might look very trivial at this point. We'll do an example where these will come in handy. Similarly, some more definitions. We have a space which is a set. So of course we can have a subset which will be a subspace. And it is defined as such that if there is a subset W of a vector space V, it itself is a vector space under the operations of vector addition and scalar multiplication, and then it can be called a subspace. And the criteria to check whether a subspace is indeed a subspace or not, it must satisfy instead of 10 only two axioms. Why? Because being a part of the larger or the superset V, it will already inherit most of the properties. Still, just to be rigorous, it must further ensure or further satisfy two of the most important ones, which are if x and y are in the subset W of the vector space V or the subspace W of vector space V, then there's some x plus y should also lie in the subspace. And if x is in the subspace W and k being any scalar, the product k times x should also be in the subspace W. The definition of linear independence, this was also covered in the lectures. So a set of vectors, say x1 up to xn, so this is uh, countable finite, is said to be linearly independent if and only if the only constants satisfying the equation k1x plus k2x plus k3x and so on till knx xn equals 0 are only when each of these coefficients are equal to 0 themselves. What does it imply? This implies that there is no set of coefficients for which a linear sum of all the vectors multiplied by the coefficients will equal the zero vector. Okay, so say if you have a question where you are provided a set of vectors, say three vectors, and you are asked to examine whether they are linearly independent or dependent. It's very easy to show the lack of independency, as in you just have to find one case where, say, multiplying them by any coefficients, any say combination of these vectors. Let this be u2, let this be u3. So say c1 u1 plus c2 u2 plus c3 u3 equals 0. This might even be very easy to do analytically if, say, the vectors are of smaller dimensions, or rather simplistic, say whole numbers or yeah, whole numbers are negative integers and so on. But as the dimensions of the vectors grow, this analytical process may not be, say, very convenient. in which case we'll have to resort to some other analytical means of determining whether a given set of vectors does constitute a linearly independent set or not. We'll also look at into a few examples of those kind. Uh, so this was for a finite countable set. What happens if the set is uh, countable but not finite? That is, it goes on infinitely, however, still countable. So in such a case, if you have an infinite set of vectors S, which contains the vectors x1, x2, x3, and so on till infinity, it will be called linearly independent if every finite subset of the set S is linearly independent in itself. And if any of the subsets of any of the finite subsets of S is not linearly independent, then the superset will be called linearly dependent. The linear dependence or independence has implications when we are trying to solve linear systems of the form Ax equals b or Ax equals 0. And as the course progresses, we'll look into what those implications are and what we can predict about the nature of the solution, its very existence from these conditions. Some more dimensions, some more definitions on the basis, the dimension, and span. So for a set of vectors b equals x1, x2 till xn in a vector space V, if the set B is linearly independent, and if every vector in the vector space V can be expressed as a linear combination of these vectors, then B is said to be a basis for V. Thus, a basis is perhaps the very fundamental building block of a vector space, say for three-dimensional Cartesian coordinate system or for 3D Cartesian space. The basis vectors are simply I hat, j hat, or k hat. Because any vector in this 3D space can be expressed as a say a linear combination of these three. So we will have say a1 I hat plus a2 j hat plus a3 k hat, and based on the varying the parameter, that is the values of these a1, a2, and a3, you can express any vector in 3D space using these three basis vectors. Of course, for three-dimensional space, the basis vectors, sorry, so 1, 0, 0, 0, 1, 0, and 0, 0, 1. We see that these are linearly independent because there is no way that I can simply multiply each of them with some scalar and add them up in any way to obtain a zero vector. Similarly, for any n-dimensional vector space, you can have a basis, and every vector in that vector space will be expressible as a linear combination of the elements of the basis vector set. The dimension of a vector space is again defined on the utilizing the basis. So the number of vectors in the basis for vector space V is said to be the dimension of the space. So for 3D Cartesian space, our basis vector space has these three vectors I hat, j hat, and k hat. So the dimension of the space is 3, or as we write it, R3. The span. So if S denotes any set of vectors x1 till xn in a vector space, then the set of all the linear combinations of the vectors, say expressed as k1 x1 plus k2 x2 plus kn xn, where ki are scalars, is called the span of the vectors and written as span of S. Again, the set of vectors in a vector space V is a basis for V if S is linearly independent and is a spanning set for V. And the number of vectors in this spanning set is the dimension of the space B. Some of us might be new to these definitions, and we might not have encountered them during our regular, say, engineering mathematics courses. Some of the more rigorous concepts may not have been introduced, say at a bachelor's or even at a master's level. and we might not even see much use for them. However, in the purview of this course, these topics are introduced, and it helps if you go over just the definitions. Again, some simple recapitulation of matrices, especially matrix multiplication. The important thing to note is that when this multiplication is defined and when it is not. So when we have two matrices, say A having m rows and p columns, so and B having p rows and n columns, then the product is defined, and it is defined only for the multiplication AB, because uh, so it's AM cross P times B, P cross M. So only because the the number of columns of A is equal to the number of rows of B. Only then is this multiplication defined. Say if it were the other way around, if I'm trying to obtain or see what the multiplication BA yields, so the dimensions are as such, and we see that the number of columns of B is not equal to number of rows of A. Thus, this is not defined. And how to perform a matrix multiplication, I believe all of us are well aware. So I'll not go into that again. Some very fundamental properties of, say, the transpose of the rank and such, which will help us with the assignment. So for two matrices A and B and the scalar K, we have the transpose of A transpose equals A plus B transpose shall equal A transpose plus B transpose, which is the transpose of a sum. For AB transpose, you have B transpose A transpose, and multiplication by a scalar does not affect anything. So, I mean, it still remains the same. So, Ka whole transpose shall equal K times A transpose. And important parameter is often the rank of the matrix. So, the rank of an M cross N matrix A, denoted by rank of A or even sometimes R, is the maximum number of linearly independent row vectors in A. This is important. It's the maximum number of linearly independent row vectors. So if we could come up with a way to determine how many rows of a matrix are linearly independent, we can then comment on the rank of a matrix. And we'll just look into a few methods of doing this. Thus, the rank can be obtained by a procedure called row reduction, where we perform some elementary row operations. So I believe there are three elementary row operations. One is interchanging any two rows of a matrix. So it's denoted as Rij. So where the I and j rows are interchanged. Uh, the next one is scalar multiplication. So you have say Ri goes to k Ri, where you multiply any row by a scalar. And the third is of course say linear combination of those, or addition of rows uh, with after multiplication with some scalar. So say your ith row can be transformed as such. So say C1 Ri plus C2 Rj. These are some of the common notations we use. The notations may be different across different textbooks, but the meaning remains the same. And utilizing these elementary row operations, we can obtain the row reduced form. And it is a theorem that if matrix A is row equivalent to a row echelon form B, what the row echelon form is, we'll look at in the next few slides. So if this condition were to be true, then the row space of A shall equal the row space of B. Similarly, there are theorems regarding the column spaces, which were discussed in the lecture. It would be a good idea to look them up. Again, the non-zero rows of B form a basis for the row space of A. This will come in handy in the upcoming weeks when we try to determine the basis of linear systems. And the rank of A shall equal the number of non-zero rows in B. Thus, if you want to determine the rank of a matrix, we'll perform certain elementary row operations on it. We'll try to achieve a row reduced echelon form. And then from that row reduced echelon form, depending on the number of non-zero rows present in that form, we can comment on the rank of the matrix of our original matrix. And the relationship is that the rank of the original matrix A shall equal the number of non-zero rows in the row reduced echelon form B. To obtain the row reduced or row echelon forms, we perform certain elimination operations. Two of the most common ones are Gaussian elimination and Gauss-Jordan elimination. You might even have read about them and implemented them in code uh, during your, say, bachelor's or master's level numerical methods courses. So this will just be a quick recap. And the fundamental idea here is that when we are trying to solve a system, so you have any system like say a11 x1 plus a12 x2 plus a13 x3 equals b1. So just your say usual or arbitrary system ax equals b. I'm just writing it out. We write it in matrix form as where the three matrices are. So in print, these vectors are written in bold form. In writing, we often utilize the tilde. So whenever we are trying to solve a linear system of this kind, we want to obtain the solutions, of course, should they exist, for these three variables, x1, x2, and x3, or x, y, and z, and or whatever you might use. And solving these three equations simultaneously while we have been doing it is cumbersome. So any software package, such as say MATLAB, which operates entirely on matrix operations, what it does is it tries to eliminate some of these numbers from the coefficient matrix. Say if uh, it were to happen that these two numbers went to zero, and of course this would also be modified in such case, you would find that this new equation would simply be 0x1 plus 0x2 plus some, say, modified A33x3 equals some modified B3. Then you would have a direct solution for x3. Similarly, for the other cases. And that is what we try to do perform by elimination. So these diagonal elements or the principal diagonal elements in such a case are utilized as pivots. That can only happen if they are non-zero. If they are zero, then things get a little different and we have to resort to other techniques. But I mean, in the ideal case, when everything is fine and your system is really easy to work with, you will try to preserve these pivotal elements and then utilize them to eliminate these other, say, lower triangular elements and put them to zero. And that is what we try to do with this elimination methods such as Gaussian elimination or Gauss-Jordan. Once we are done with this, we obtain solutions for the systems. For the Gaussian method, we have to perform back substitution. So say you obtained x3, you put it in this equation again. So you have some coefficient times x2 plus some coefficient times x3. You already know x3, you know the coefficients, you know the RHS, so you obtain x2. Then substitute both x2 and x3 in this first row. And now you have solutions, should they exist, for all three variables. So for obtaining the row echelon form, by the Gaussian elimination. We row reduce the augmented matrix uh, to and perform row operations till the row echelon form is obtained. The form is characterized by these three features. So for the row echelon form, the first non-zero entry in a non-zero row is 1. In consecutive non-zero rows, the first entry 1 in the lower row appears to the right of 1 in the higher row. So if your first row looks something like this, your second row should have the 1 here. They should ideally be 0. This will have some other number. And this is for, of course, a 3 by 3 case. As your dimensions increase, this will just follow. And the rows consisting of all zeros are shifted to the bottom of the matrix. So say if you, by some elementary row operations, you arrive at a row which has 0 in all the places, you simply exchange it to the bottommost position. Then the final, say, form of the transformed or operated matrix that you obtain will be called a row echelon form. Further, there is a reduced row echelon form obtained by the Gauss-Jordan method, where we obtain an augmented matrix that has all these properties and the additional property that a column containing a first entry 1 has zeros everywhere else. We'll work with an example where we utilize both the Gaussian elimination and the Gauss-Jordan elimination to solve a linear system. Then I hope this becomes clearer. And I believe we have the last recap slide. So some fundamental properties of the inverse of matrices. So should A and B be two matrices which are invertible, that is, they are non-singular, then the inverse of A inverse should equal A. The inverse of the product AB shall equal, so AB inverse shall equal B inverse A inverse. As we are well aware, uh, the matrix multiplication is not commutative. So pre-multiplication and post-multiplication do not arrive necessarily or generally arrive at the same product. So A times B is not equals B times A. So AB inverse equals B inverse A inverse. And the inverse of a transpose of A shall equal the transpose of the inverse of A. Again, for any general linear system, AX equals 0. So a homogeneous system is homogeneous when your B matrix is essentially a 0 matrix or it has only 0 elements. So the right side is 0. A homogeneous system is always consistent and thus it will have solutions. It can have a unique solution if the rank of A equals the number of columns. So is a matrix of dimensions m cross n. If the rank of A equals the number of columns, then the solution for Ax equals 0 will be unique. That is, you will have only one solution. However, if the rank of A is less than n, so let's denote the rank of A as R. So if R is less than n, then you will have infinitely many solutions with n minus R number of arbitrary parameters. So depending on how you change the value of these parameters, your solution will keep differing. Thus you can come up with a family of infinite solutions. Things become a little more tricky when the right side is not zero. So say you have something on the right side, x equals b. This is called a non-homogeneous system. For a non-homogeneous system, first we must always check for the consistency. And it will be consistent if the rank of the original matrix equals the rank of the augmented matrix, or inconsistent if the rank of A is less than the rank of the augmented matrix. So if it is inconsistent, there will be no solutions. If it is consistent, then again we check the relationship between the rank and the column dimension. So if the rank of A equals the number of columns, then the solution is unique. However, if the rank of A is less than the number of columns, you will again have some arbitrary parameters, which in this case would be the difference between the number of rows and the rank. And depending on what values you supply for these parameters, your family of solutions will keep changing because you can come up with an infinitely large family of solutions for your case. Now we'll look into a few questions which utilize these concepts and will be relevant to the assignments that we looked at this week, that is due for this week. So for the first question, consider the set V of positive real numbers. If x and y denote positive real numbers, we write the vectors in V as the vector x is equals simply x and the vector y equals y. So this is the definition of the subspace that you are, of the vector space that we are working with. Again, they have defined the addition as well. So the addition is defined as the vector x plus vector y equals xy. So the addition of the two vectors will actually produce the product of the two positive real numbers. And the multiplication is defined as any scalar k times the vector x actually equals the positive real number x raised to the power k. So as I was discussing, not your classical definition of multiplication and addition. So in such a mathematical framework where the preliminary operations or the elementary operations are defined as such, we have to determine whether the set vector set we are working with is a vector space or not. To determine this, of course, we'll look at the axioms that must be satisfied. So there are 10 of them. And even if one of them is violated, the set is not a vector space. So we'll have to check individually for all the 10 axioms. So let's do that. So I'll list down each axiom one by one and then we'll check whether the axiom is getting satisfied or not. So the first axiom went something like this. If x and y are in the vector space V, then their sum should also lie in V. So let us check if this holds. So in this case, we have the numbers are positive real, so they are greater than zero. So say, and they're defined as such. So the vector x simply denotes the positive real number, which is greater than zero. Similarly for y, the sum is defined as their product. Since each of them are individually greater than zero, we know that their product will also be greater than zero. Thus, we see that indeed the sum x plus y lies in the vector space V or or just erase this for the two elements x and y lying in V. Thus, this first axiom is satisfied. The second axiom went like this. So for all vectors x and y in the vector space V, the sum should be commutative. So x plus y should equal y plus x. Let's see if this hold. We know that greater than zero, again, the vector y also denotes the positive real number y. And we know that for positive real numbers, xy equals yx. That is, the product is commutative. So we say that x plus y shall equal xy, which shall equal yx, which can indeed be written as the sum of y vector and x vector. So even this is satisfied. Third axiom that for all x, y, and z in the vector space V, the sum should be associative. So x plus the sum of y plus z should equal the sum of x plus y plus z. Again, based on the addition which has been defined here, x is greater than 0, y is also positive real, and so will be z because it is an element of the vector space V. So we will have x plus y plus z equals xy. So z vector shall equal xyz shall equal xyz, which will be, say, something like, and you know the drill. So which shall equal. So even this is satisfied. So we are looking for that one axiom which is violated. Then we can condemn this supposed vector space to being not a vector space. However, our search continues. The fourth axiom regards or is related to the existence of the unique zero vector. So there exists a unique vector zero in the same vector space such that the zero vector plus x vector for any element x of the vector space shall equal the x vector plus the zero vector, which will in turn equal the vector itself. So let us see if such a vector can be found in this case. For the set of real numbers, the additive identity is simply 0, the multiplicative identity is simply 1. But here we see that the addition operation itself is defined in a way that, so if our zero matrix were say just 0, then I would have 0 plus x equals 0 times x because it is defined as multiplication, which shall equal 0 and not the original element itself. So clearly 0 is not the unique 0 vector. What can be the vector? Let us look at the element 1. So if I have this 1 vector, it simply has the element 1. And if I add it to any vector x, so I have 1 times x, which equals x times 1, which equals x. So we see that this one vector, which I am so calling, is actually the 0 vector. So the 0 vector is again a name holder or a placeholder. It does not necessarily mean 0, and it is just like the identity matrix is defined by I. The 0 vector is called 0 vector and denoted by the 0. But in this case, it will have the value 1. So it does exist. So even this axiom is satisfied. Let us examine or test for the fifth axiom. So for each vector x in the vector space V, there exists a vector minus x such that their sum will of course be commutative, which shall equal the zero vector. Now, just like in the previous case, the zero vector was not, say, zero itself, or its elements were not zero. Similarly, in this case, the negative vector or the negative of any vector in the vector space need not be just, say, minus one times our original vector. And that is because of the way the vector addition and scalar multiplication have been defined in this case. So let's see if it were so that I am just, so if my this negative vector were just minus x, so let's see what happens if I add them. So this would be x times minus x, because that is how we have defined our addition. It will just be minus x square. But we already know that our zero vector is actually 1. So this is clearly not the candidate. However, can we come up with some other vector one which will satisfy this property? So if we define the negative vector as equal to the reciprocal of the magnitude of the original vector and perform this operation, then let's see what happens. And we recollect that indeed 1 was our zero vector in this case. So there does exist such a negative vector, which in this case will be the reciprocal of the magnitude of the original, and thus even this fifth axiom is satisfied. So we have already satisfied all the axioms for the vector addition. Now we'll check for the axioms corresponding to scalar multiplication. The sixth axiom that for any scalar k, if the vector x is in V, then the scalar product k times x should also be in V. So let's check if this is satisfied. Remember that we have defined scalar multiplication like this. So k times the scalar k times any vector x shall equals the positive real number x raised to the power k. So for any scalar k, so if k is any scalar, and as we know for our case, the vector space consists of only positive real numbers. So it's x greater than 0. Then k times x shall equal x power k, which is greater than 0, is also in the same vector space. So this is satisfied. If it were to happen that we ended up, after performing this operation, we ended up, say, with a negative number or with 0, then it would no longer lie in the original vector space V, and thus this axiom would have been, say, not satisfied or violated. The seventh axiom of scalar multiplication. So if k times x plus y shall equal kx plus ky. Let's check for any scalar k based on how we have defined the scalar multiplication in our case. So x plus y is equal to xy, and the multiplication term means we raise it to the exponent. This again means k, x power k and y power k, because they are just positive real numbers. But x power k, if you remember our definition, is nothing but k times x vector. and these are multiplied. So it's actually the vector sum. So we see that even this one is satisfied. These things might look abstract at some point, and that's why I said that it's important to be thorough with the definition and not think too much about the physical implications as we are still at the abstract stage and be rigorous. That will help. Once we go more into the application areas, is where we'll start to try to make sense of what the physical implication of any of this is. For now, the mathematics is abstract. The eighth axiom for multiplication of a vector by sum of scalars k1 and k2, they should equal associative property of the scalars. Let's check if this holds. So for our case, based on how we have defined scalar multiplication, this will simply be x power k1 plus k2, which will equal x power k1 times x power k2. And depending on how we have, uh, say, defined the vector multiplication or vector addition, this is indeed, say, x vector times k1 plus x vector time k2. And depending on how, or on the basis of how we have defined this scalar multiplication, this indeed is k1 x1 plus k2 k1x times k2x. So this is satisfied as well. Two axioms to go. The ninth axiom says that k1 times k2x should equals k1 k2 times x. So associative property of scalar multiplication. And let's see what this looks like. So the LHS, if you work on it, would mean say k1 times x power k2. Again, based on how we have defined scalar multiplication times k1, which indeed equals x times k1 k2, which is nothing but k1 k2 times the scalar x. So this is satisfied as well. And things looking good so far. Let us just check for the final axiom and whether it is satisfied or not. 1 times x vector should equals x vector. 1 being the scalar here. So we have defined kx as x power k. So 1 times x shall equal x power 1 shall equal x, which again is equivalent to the vector of this vector space element. Thus, we see that all the axioms are satisfied. Thus, since all the axioms are satisfied, we conclude that V is indeed a vector space. So we saw that how to check whether any set of vectors is indeed a vector space or not. We have to check individually for all of the 10 axioms to be satisfied. And if that turns out to be true, the set can indeed be called a vector space. We will take a short break here and reconvene to solve the rest of the problems. It's 7:10 now, so let us meet around 7:15. Hi and welcome back. Let us continue from where we left off. The second question is asking us to examine whether the given sets of vectors are linearly independent or dependent. So there are two sets. The first is 1 comma 1, 0 comma 1 and 2 comma 5. As we were saying, from the definition of linear independence, is if we can come up with a set of coefficients k1, k2 till kn such that the sum k1 x1 plus k2 x2 plus k3 x3 and so on equals 0. For a case where not all of the coefficients are 0, then the set of vectors will be linearly dependent. If not, it's independent. And I mentioned that it is rather straightforward or easy to do in certain cases when the vectors are simple, such as this. So we'll do this by simple visualization or inspection. So we have the vectors 1, 1, 0, 1, and 2, 5. So if I were to leave it as such, multiply this by minus 2, I see that adding this 2 plus 0 minus 2 is 0. So the top, I mean the first element is 0 already. And to get the second element as 0, I have 5 minus 2, 3 and minus 3. So I have 5 minus 3 minus 2 is 0. So I see that for this set of coefficients which are not all 0, so minus 2 times 1 1 minus 3 times 0 1 plus 1 times 2 5 is indeed 0 0. Thus, the set is linearly dependent. Finding just this one set of coefficients is sufficient. We can also find another set. So if we just want to cheat our way through, we can have it say rather than negatives, these coefficients can be positive, and I can have minus 1 here. So this is another set of coefficients for which the set is linearly dependent. So it does not matter as long as we found just one. Now, this was for case A. For case B, the vectors are not so straightforward to work with. I mean, they might be. If we just put in a little effort, look at the coefficients, how they interact, we may be able to come up with a coefficients for which the linear combination may yield 0. However, it need not be rigorous. And just because you or I could not think or could not come up with a set of coefficients which produces a linear combination equaling 0 does not mean it does not exist. So the absence of evidence is not evidence of absence. A more rigorous way to do this would be by determining the rank and checking uh, if how that relates or how that compares to the number of vectors we have. So in this case, we have three vectors. Let us put them as rows of matrix, say A, and then if the rank of A, say equal to R, equals the number of vectors, which is 3, then this would imply, or it would be implied by the fact that they are linearly independent. So uh, let's see. First, let us put the three vectors as rows of the matrices. So 1, 2, 3, 1 over 1, and 1 minus 1, 5. Now, we'll perform some elementary row operations and produce a row reduced form to find the rank. So usually the way we do it is, as I spoke, we want to preserve the diagonal elements at pivots. We find that We usually leave the first row unchanged unless there's a problem with it. So here the first row is just fine. We just leave it as is and we transform the other rows. So I want a 0 in this position. So what I'll do is my row 2 changes as row 2 minus row 1. So 1 minus 1 0. 0 minus 2 is minus 2 and 1 minus 3 is minus 2 again. Similarly, I want 0 here. So R3 will also change as R3 minus R2. So 1 minus 1 0 minus 1 minus 2 is minus 3 and 5 minus 3 is 2. For the next set of operations, I would want a 0 here. So as to produce a strictly upper diagonal matrix. So I leave R1 and R2 as is. My R3 will change as R3 minus 3 by 2 times R2. And what this will yield is 1, 2, 3, 0 minus 2 minus 2, 0 minus 0, 0 minus 3. This becomes plus 3 by 2 into 3, so 0. And 2 plus 3 by 2, so 5. Again, I mean, this is just okay to work with, but for the sake of, say, convenience, we can just do one more transformation, which will be nothing but just a scalar multiplication of the rows. So I just uh, my second row is transform multiplied by minus half, and the third row by 1/5. This will yield 1, 2, 3, 0, 1, 1, 0, 0, 1. Now we see that these three rows are linearly independent, and in this is the row reduced form or the row echelon form. In the row echelon form, I found that I have three non-zero rows, which would imply that the rank is equal to 3. We came across this definition where the rank of the original matrix shall equal the number of non-zero rows in the row reduced matrix B. And again, we saw how the if the rank of A equals the number of vectors we are originally examining, which is 3 in this case, the vectors are linearly independent. Thus, organizing the vectors given to us as the rows of a matrix, then performing elementary row operations on the matrix to obtain the reduced or the row echelon form, and checking for the rank of that reduced matrix can actually help us in rigorously determining whether a given set of vectors are linearly independent or dependent. The third question is asking whether for a, it describes a scenario that a given matrix B is subjected to right-hand multiplication of permutation matrix and what changes can be observed. So if you would recollect from the lectures, when we pre-multiply a given matrix by the square permutation matrix, so I believe often the permutation matrix is just the identity matrix, the square identity matrix. In the case of a pre-multiplication, the rows are changed. I, I believe like this. Yes. This was covered in the lectures, but this refers to a pre-multiplication or left hand multiplication. Similarly, we'll find that for a right hand multiplication or a post multiplication, it is in fact the columns that change. Thus, it is the columns which will be permuted and we'll observe changes in the columns for the case of post multiplication. For pre multiplication or left hand multiplication, the rows are changed. The fourth question is asking us to solve for this matrix multiplication AB, B inverse, A inverse. So, from the properties of matrices, okay, let us scrap this question for now because maybe this is not always generally true. So, we'll discuss this in the next week. For now, let us skip over it because yeah, an exception came to my mind. The fifth question, which says that A is a 4 cross 3 matrix and B is a 4 cross 4 matrix. So we have two matrices. And what would be the dimensions of the resultant matrix AB and BA? Now A has dimensions 4 cross 3, B has dimensions 4 cross 4. For the product AB, we find that the number of columns of A is not equal to the number of rows of B. Thus, this is not defined. For the second product, BA, so B has dimensions 4 cross 4, A has dimensions 4 cross 3. We find that the number of columns of B is indeed equal to the number of rows of A. So the matrix multiplication or the matrix product is defined and we can proceed to find the dimensions. And we'll find that BA will have dimensions of 4 cross 3. So the answer in this case would be 4 cross 3. The sixth question says that suppose there is a matrix A of dimensions 4 cross 3 and it has only one vector as the basis for its null space. Determine the rank of A. Now again, this theorem, it's commonly called the rank nullity theorem. This was discussed in class, and I'll just like to revise what it was. So it says that the rank of A plus the nullity of A, that is the dimension of the null space. The dimension, of course, will be equal to the number of elements of the basis vector. The sum of the rank and the nullity of A shall equal the number of columns of A. Or if we use the usual notations, so R plus say S for nullity shall equal N for a matrix A of dimensions M cross N. Here we find that we are supplied with the dimensions M and N. So M is 4, N is 3. Only one vector is in the basis of the null space. So S is 1. And we are to solve for R, that is the rank. So the rank will be equal to nothing but N minus S, is equal to 3 minus 1, which is 2. So the rank of A in this case is 2. So option C is the correct answer. This theorem is important to note. It's called the rank nullity theorem and says that the sum of the rank and the nullity of a matrix A shall equal the number of columns of A. We're not really looking into proofs during these sessions, but if someone is interested, they might refer to the standard texts which are recommended by Professor. For the next question, suppose A is an M cross N square matrix such that the rank R of A is less than N, N being the dimension of the columns, or the column dimension, sorry. Uh, then for the consistent system AX equals B, what will be the number of solutions? Now this is again another straightforward question which can be say answered by simple visualization or simple revision of the concepts. So we had this helpful chart here. For a homogeneous system x equals 0, it is always consistent. Here we are working with a non-homogeneous system where the RHS B is not necessarily equal to 0. And we are also told in the question that the system is consistent. That is already supplied to us. That, so the rank of A would have been equal to the rank of A augmented B matrix. And in this case, if the rank equals the column dimension n, then the solution is unique. If not, then there are infinitely many solutions. So for our case, we have A is n cross n, R is less than n, it is consistent. So there will be n minus r independent parameters. And depending on the values which we assign to these independent parameters, our solutions will keep changing, and thus will obtain an entire family of solutions, which will be infinitely many. So option A is correct. For the eighth question, we are supplied with a linear system. 2x1 plus 6x2 plus x3 equals 7. x1 plus 2x2 minus x3 equals minus 1. 5x1 plus 7x2 minus 4x3 equals 9. And we are to solve it using first Gaussian elimination and second the Gauss-Jordan elimination. Now, I already checked that this system is consistent and that it has a unique solution. So we can move ahead with those assumptions. Otherwise, say we would have to first check whether or not the system itself is consistent, and then we would be able to judge. We would have to judge the existence and nature of the solutions, whether it's unique or whether there are infinitely many solutions. For this case, we already know that the system is consistent and the solution is unique. So first, let us write it in the familiar matrix form. So you have the coefficient matrix 2, 6, 1, 1, 2, minus 1, 5, 7, and minus 4. You have the variable vector x1, x2, x3, and you have the RHS or B vector. 7 minus 1, 9. The first step is to write the augmented matrix. So we just add another column to the matrix A. This column contains elements from the vector B. So 2, 6, 1, and generally augmented matrix is denoted by such a dotted line. It can also be a solid line in some textbooks. And 7, 1, 2, minus 1, minus 1, 5, 7, minus 4, and 9. This is my augmented matrix. And now I'll perform a few, say, elementary row operations to arrive at the row echelon form. So I first of all I notice that I already have a 1. So maybe I'll just exchange the rows. So R2 and R1 are exchanged. So 1, 2, minus 1, 2, 6, 1, 7, 5, 7, minus 4, and 9. Now I'll try to say have 0 in these locations. So R2 can be transformed as R2 minus twice R1. R1 will be left untouched. So 1, 2, minus 1, minus 1. R2 minus 2, R1, so 2 minus 2 is 0. 6 minus 4, 2. 1 plus 2 shall equal 3. 7 plus 2 shall equal 9. And similarly, for the third row, I can have R3 minus 5, R1. So 5 minus 5 is 0. 7 minus 10 is minus 3. Minus 4 plus 5 is 1. And 9 plus 5 is 14. So this is accomplished. Now for the row reduced form, I know that the first non-zero entry should be 1. So I would like a 1 here. I will just multiply the second row by half. So the thing about this row echelon form is that it's not unique. Depending on what set of operations or what sequence of operations you perform, you can end up with different row echelon forms, which are all equivalent. That is the end product of the Gaussian elimination is not unique, and depending on how we approach it, we can end up with different matrices, which will, however, all yield the same result. The thing with the reduced row echelon form that we obtain after the Gauss-Jordan elimination is that it is unique. So, irrespective of what sequence of operations we perform to get there, we'll always arrive at the same matrix because it is unique. So 0, 1, 3 by 2, and this is 9 by 2. 0 minus 3, 1. The reason why we want 1 here is because that will be helpful to eliminate this element. So now I can just transform the third row as uh, R3 plus 3 times R2. What that will yield is 1, 2, minus 1, minus 1, 0, 1, 3 by 2, 9 by 2, 0, minus 3 plus 3, 0. 1 plus 9 by 2 will be 11 by 2, and 14 plus 27 by 2 will be 55 by 2. I'll just rewrite that matrix here for clarity. So 1, 2, minus 1, minus 1, 0, 1, 3 by 2, 9 by 2, 0, 0, 11 by 2, 55 by 2. And just to turn these into whole numbers, so I'll multiply R2 by 2 and also R3 by 2. Or that might not even be necessary since I already have two zeros in the last row. I can simply multiply it by 2 by 11. So R3 goes to 2 by 11 times R3, or it transforms as such. So I have 1, 2, minus 1, minus 1, 0, 1, 3 by 2, 9 by 2, and 0 0 into 1 and into 2 by 11, so 5. And what this actually means is that now my system has been transformed as 1x1 plus 2x2 minus x3 equals minus 1, 0x1 plus 1x2 plus 3 by 2 x3 is 9 by 2, and 0x1 plus 0x2 plus x3 is 5. So this is a direct result, x3 equals 5. We back substitute it into the previous equation. So x2 plus 3 by 2 into 5 is 9 by 2. If multiply by 2 everywhere, I have 2x2 plus 15 equals 9. So x2 is minus 6. So x2 is minus 3. Back substitute it again. So x1 plus 2 into minus 3 minus 5 is minus 1. So x1 is minus 1 plus 5 plus 6, which is equal to 10. So my solution is x1, x2, x3 equals 10 minus 3 and 5. I already have my solution. This was obtained by Gaussian elimination, where we reduced the performed elementary row operation to obtain the row echelon form of the matrix. However, the Gauss-Jordan elimination goes one step further to obtain what is called the reduced row echelon form. And the advantage in this case, in the case, would be we'll be avoiding this back substitution step. There's another one here. Now, for a relatively simple system such as the one we are working with, this does not sound like a lot. I mean, it's just say substituting one more value and computing the others. But imagine working on a complicated system which is very large and which will have computational errors, rounding off, truncation errors at every step. Also, the computational effort of actually performing the back substitution for each equation that we have. And we find that now the computational effort will be immense. So if there were any way to eliminate that extra effort that we're putting into uh, for finding the solutions, it would be very helpful indeed, and that is where the Gauss-Jordan elimination comes in. So let us just rewrite this last matrix that we had. So it's 1, 2, minus 1, 2, minus 1, minus 1, 0, 1, 3 by 2. I believe this was 9 by 2, 0, 0, 1, 5. And the difference between the Gaussian and Gauss-Jordan elimination, as we already looked at, is that for the reduced row echelon form obtained from the Gauss-Jordan elimination, the column containing first entry 0 should have zeros everywhere else. Let us try to obtain that. So we'll try to eliminate all other elements and just have preserve these diagonal elements. There need not be one. There can be some other uh, numbers also, but we'll find that anyway if we just multiply with a scalar, we can reduce it to 1. And that how it will solve the problem of back substitution is that if you have 0 in all the other places, it's simply one whatever you end up on the right with. So say if you end up with this form identity matrix on the left and some augmented or some transformed elements on the right, you actually have the direct solution, that is x1 equals b1, x2 equals b2, and x3 equals b3, because all these other elements are 0 in this case. That's what we are trying to achieve here. So, yeah. So I transform R2 such that R2 minus 3 by 2 R3. So this element will go to 0. Leave the first row untouched for now. 0 minus 0, 0. 1 minus 0, 1. 3 by 2 minus 3 by 2 is 0. And 9 by 2 minus 15 by 2 will be minus 6 by 2. So minus 3. 0, 0, 1, 5. The third row already has zeros in two places. So now we have to eliminate the elements from the first row. So is there a way to do it? If we perform, if we add the third row to the first row, then we will have the third row is untouched, the second row is untouched. 1 plus 0 is 1, 2 plus 0 is 2, minus 1 plus 1 is 0, 5 minus 1 is 4. And now to bring this element to 0, if we just subtract twice the second row. So I will have the second row untouched, the third row untouched, and R1 minus 2 R2. So 1 minus 0 is 0, 2 minus 1 minus 0 is 1, 2 minus 2 is 0, 0 minus 0 is 0, and 4 minus 2 into minus 3, 4 plus 6 is 10. And now I see that I have obtained the identity matrix on the left and the transformed B matrix on the right. And this means that 1x1 plus 0x2 plus 0x3 is 10. 0x1 plus 1x2 plus 0x3 is minus 3. 0x1 plus 0x2 plus 1x3 is 5, which directly yields the solutions as x1 equals 10, x2 equals minus 3, and x3 equals 5. And we noticed how no back substitution was needed in this case. And as we can guess, definitely the computational advantage of avoiding this back substitution step will scale up with the size of the system we are working with. So the larger the system, the more efficient the Gauss-Jordan method will be. So these are the questions I had for today, and this is the content I intended to cover. So if any of you have any doubts, and now would be the time to ask them.
Hi, Sourav.
Hey Anirudh.
Yeah, hi. So, in the last step that you just derived using Gauss Jordan, right?
Yes, yes.
So in that case, that matrix is the inverse as well for that, right?
Okay, it might be, I'm not sure if that will be generally true. It might be true for this case, but whether that is generally true or not, I'll have to check.
Okay.
Yes.
And I also have two more questions.
Yes, yes.
So the first one is that like when we conclude vectors stating that it's linearly independent or dependent, so
Yes.
what does that imply to the application of that statement or something in can you correlate that with some example?
Yes, one of the examples which I'm directly off the top of my head is that say you are given three vectors which are in the column space of a given matrix.
Okay.
And yeah, if those three vectors are linearly independent, then they can also form the basis of that vector space. So every other vector in that vector space can be defined or can be shown to be a linear, just a linear combination of the basis vectors. But if
Okay.
the three given vectors are not linearly dependent, if one can be expressed as a linear combination of the other two, then those three vectors, even if they're a subset of the column space, they are not a basis.
So what do you mean by basis? Actually, I missed that, I guess.
Basis vector is so for say for example for 3D space you have this I hat, j hat, and k hat. So
Okay.
any other vector in this 3D space can actually be expressed as a linear combination of I, j, and k. So
Yeah.
this I, j, and k can actually form the basis. So they are like the fundamental building block of this 3D
Okay.
vector space. Yeah. To
Okay.
yes.
Got it.
So yeah,
So
yeah. So we can check with for any other set of vectors whether they form the basis or not using this linear dependence or independence.
okay. Okay. Got it. Yeah. And my next question is that so we are actually like defining the vector space dimension using R and then to the power of the dimension, right? Like for R3 or something like that that you were mentioning.
Yes.
So is it always that we need to mention it as a dimension of row and not as a dimension of column?
So usually like depicting it with this R with some superscript. This is the
Yeah.
common notation. But if you ask me, I'll be honest, I am not sure if this actually means the rows. This can just be like say
Okay.
yeah. So I am not really sure if this always refers to the rows as such.
Okay. Okay.
Yes.
Got
So
it. Yeah.
you can check with the professor or maybe some standard textbook. I'm not really sure.
Sure. And like, can you like give a intuitive like visualization for the vector space, subspace, and then the null space? Because I just want to understand like how they look. Like apart from the definition, like could you give an example like to define these three vector space, null space, and subspace?
Uh, Sure. So I'll just add a couple of slides on those topics for the next week. I
Okay.
don't have
Sure.
anything handy right now, but I'll definitely add, say, a couple of slides on them for the next week.
Okay.
Yes.
Sure. So is this slide available for us? Like whatever you just presented?
Yes, yes. I'll be uploading this, and the like NPTEL will be sharing it or making it available to you guys.
Okay. Yeah,
Yes.
that should be good. Yeah. Yeah. So yeah, that's it from my side. Yeah.
Okay. Thanks, Anirudh.
Yeah. Thank you, sir.
So if there are no further questions, we can conclude this session.
Okay.
Okay.
Thank you.
Okay,
Thanks
thank
for
you.
joining in. Yes. See you next week.
Yeah. Thank you. Bye.